Find somewhere comfortable tonight. You don't need to follow any of this closely. You don't need to hold on to the details or remember where we've been. Just let the words come in gently, the way sound drifts through an open window at night, present for a moment, then gone, and that is perfectly fine. We're going somewhere quiet this evening, somewhere old, a place where the rock has been sitting in the sun for so long that the sun itself has left a mark. We're going to the desert, to the canyon walls, to the slow and patient darkness that has been settling onto stone for longer than our species has existed. You don't need to picture it vividly. You don't need to concentrate. If your eyes are already heavy, let them be heavy. If your mind wants to drift ahead of the words or fall behind them, let it go wherever it likes. The story will be here, soft and unhurried, and you can take as much or as little of it as you need. We're in no particular hurry tonight. The rock certainly isn't. Imagine, if you can, standing at the foot of a canyon wall somewhere in the American Southwest. Utah, perhaps, or Arizona. The kind of place where the air is dry enough that the inside of your nose feels slightly papery, and the light in the late afternoon turns everything the color of warm copper. The rock face in front of you is enormous. It rises maybe 60, maybe 100 meters above you, and it has been here in one form or another for millions of years. At its base, where boots have scuffed and rain has occasionally pooled, the stone is a pale sandy color, the true color of the sandstone or basalt beneath, exposed and honest. But above that, where the rock has been undisturbed for long enough, something has changed. The surface has darkened. Not uniformly, not all at once, but in long descending streaks and patches, the way moisture might run down a window and leave a faint trace behind. Some sections are a deep reddish brown, the color of dried blood or old rust. Others are darker still, almost chocolate, almost charcoal. And in places, particularly on south-facing surfaces that receive the most sun and the most time, the rock has gone very nearly black, a glossy, slightly reflective black that catches the afternoon light and gives it back in a way the bare pale stone never could. This darkness has a name. Scientists call it desert varnish, and it is one of the quieter wonders of the natural world. If you reached out and touched it, and many people do, though the oils from human skin are not especially welcomed by something that has taken 10,000 years to form, you would find it smooth. It feels as though the rock itself has simply decided to be dark, as though the darkness is part of the stone's nature rather than something applied from outside, which is, in a way, one of the first and most interesting things about it. Desert varnish is not the rock. It comes from somewhere else entirely. The coating is thin, extraordinarily thin. In most places, it measures somewhere between 1 and a few hundred micrometers, that is to say, between 1 and a few hundred millionths of a meter. To put that in terms you can hold in your mind, a single human hair is roughly 70 micrometers across. Desert varnish, in many of its thinner expressions, is thinner than that. A single hair. That is all the thickness separating the bare pale rock from the dark surface you are looking at. And yet that hair's breadth of material may represent 50,000 years of slow accumulation. 50,000 years compressed into something you could scrape away with a fingernail. What is it made of? The bulk of it, somewhere between 1/2 and 9/10 of its mass, depending on the location and the age of the deposit, is clay minerals, not clay in the familiar sense of the soft grey stuff potters use, though that is related. Clay minerals are a family of crystalline compounds, each one built from the same basic ingredients: silicon, oxygen, aluminium, sometimes iron or magnesium, arranged into flat, stacked sheets at the atomic scale. They are ancient materials, geologically speaking, produced by the slow weathering of other rocks over millions of years. And crucially, the clay minerals in desert varnish did not come from the rock they are coating. They arrived from elsewhere. They came on the wind. Embedded within that clay matrix are two other components that give desert varnish its most distinctive character: iron oxides and manganese oxides. Iron oxide, rust essentially, in various crystalline forms, produces the reddish and orange tones. Manganese oxide, a darker compound, is responsible for the deep browns and blacks. Together, these two elements, present in only trace quantities in the surrounding dust and soil, have been selectively gathered, concentrated, and locked into the surface of the rock over timescales that dwarf all of recorded history. And here is the central mystery, the thing that has puzzled geologists and chemists since Alexander von Humboldt first paused to consider it during his travels in the early 19th century, and that Charles Darwin himself attempted to investigate by scraping samples off rocks and subjecting them to chemical analysis. None of these materials, not the clay, not the iron, not the manganese, come from the rock underneath. The sandstone, or basalt, or granite beneath the varnish has its own chemistry, its own minerals, its own particular atomic architecture. The varnish is chemically distinct from its substrate. It is a foreign layer, built from material that arrived from the sky. The color of any particular patch of varnish tells you something about the conditions under which it formed. Orange and yellow varnish, relatively light in tone, is richer in iron oxides and tends to form in drier, more acidic environments. As conditions become more alkaline and more moisture is available, manganese begins to dominate and the color deepens through brown toward black. A canyon wall that shows a complex patchwork of orange streaks and dark black panels is, in a sense, a map of the microenvironments on its own surface. The places that catch more dew, the faces that drain more quickly, the ledges that shelter a slightly different chemistry from the exposed vertical faces below them. The coating is not uniform across the world either. Desert varnish has been found in the Sahara, in the Gobi, in the deserts of Australia and the Middle East, in the dry valleys of Chile and Argentina, and across vast stretches of the American Southwest. Wherever rock sits exposed in an arid or semi-arid environment, undisturbed by the fracturing of frost or the scouring of frequent rain, the slow painting tends to begin. The process is not exclusive to true deserts. Similar coatings have been documented in coastal and even some temperate regions, but it is in the great dry places where rainfall is rare and rock surfaces are stable for the longest periods that varnish grows thickest and most dramatic. There is something about standing before it that is difficult to articulate. It is not like looking at a fossil which announces its antiquity through shape and form. It is not like looking at a cave painting which speaks clearly of human intention. Desert varnish is simply there, dark and quiet, asking nothing, offering no obvious narrative. And yet the darkness you are looking at was not there when the first anatomically modern humans arrived in this landscape. It was not there when the glaciers of the last ice age were retreating. It has been accumulating in some places since before our species learned to make fire. It is one of the slowest things on Earth. And it has been going on without interruption, without urgency, without any apparent awareness of the civilizations rising and falling on the other side of the horizon for all of that time. The question of how it forms, the precise mechanism by which dust becomes a glossy dark coating on stone, turns out to be one of the more genuinely contested questions in earth science. The answer involves chemistry and physics and possibly life itself. It involves forces operating at the scale of individual atoms. And it begins, as so many things in the desert do, with the wind. The desert is never entirely still. Even on the calmest days, when the air above the canyon floor barely moves and the shadows lie sharp and unmoved for hours, there is a slow and invisible traffic happening at the surface of every exposed rock face. Not in visible quantities, not in the way a sandstorm deposits visible grit, but in the quietest possible way. Individual particles drifting down through the still air and coming to rest on whatever surface happens to be below them. This dust is the beginning of everything. The particles that matter most for desert varnish formation are clay minerals, and they are small enough that they can remain suspended in the atmosphere for days or weeks after being lifted from the ground. A grain of sand is typically somewhere between 60 and 2,000 micrometers across, large enough to feel gritty between your fingers. A clay particle is in a completely different category. Most clay mineral particles are less than 2 micrometers in their longest dimension. Some are less than half a micrometer. They are so small that the thermal motion of air molecules is enough to keep them aloft, bouncing them around in the lower atmosphere, the way smoke particles drift in a sunbeam. They can travel thousands of kilometers from their source before they finally settle. And what they are, at the atomic level, is worth understanding. Not because you need to hold the chemistry in mind, but because the structure of these minerals explains almost everything about why they are so good at building desert varnish. Clay minerals belong to a group of compounds called phyllosilicates, from the Greek word for leaf, because their structure is built from flat sheets, one stacked on another. Each sheet is made from a repeating pattern of silicon and oxygen atoms arranged into hexagonal rings, bonded to a layer of aluminium or magnesium atoms above and below. The result is a flat crystalline slab, perhaps a nanometer thick, a nanometer being 1,000th of a micrometer or 1/1000th of a meter. And those slabs are stacked in parallel, separated by tiny gaps. The specific clays found most abundantly in desert varnish include minerals called elite, smectite, and kaolinite, each with a slightly different stacking arrangement and a slightly different chemical character. What makes clay minerals so important in this story is their surface area. Because they are built from such thin, flat sheets, and because each particle is itself a stack of many such sheets, the total surface area exposed by a small quantity of clay is genuinely vast. A single gram of smectite clay can have an internal surface area of several hundred square meters, roughly the floor area of a large house folded up inside a pinch of powder. That enormous surface area is covered with electrical charges arising from the way atoms of different sizes and different numbers of electrons substitute for one another within the crystal lattice. These charges attract other charged particles and ions from the surrounding environment, the way a magnet attracts iron filings. This electrical character is why clay minerals are so good at holding on to things. When a clay particle settles onto a rock surface, it does not simply sit there passively. The charges on its surface interact with charges on the mineral grains of the rock, and with ions dissolved in any moisture present on the surface, and with other clay particles settling nearby. Over time, a thin mat of clay begins to form. Not through any deliberate process, not through any single dramatic event, but through the slow accumulation of millions of tiny electrostatic interactions, each one individually weak but collectively powerful. Now, alongside the clay, something else is arriving, dissolved in the thin films of rainwater and dew that occasionally wet the rock surface in concentrations so small they would be nearly impossible to detect with the naked eye. Come traces of iron and manganese. These elements are present in soil dust, in organic matter, in the chemistry of rain itself, as it falls through an atmosphere carrying traces of everything the wind has ever touched. They arrive as ions, atoms that have lost 1 or 2 electrons and therefore carry a positive electrical charge, dissolved in water the way salt dissolves in a glass of water. Iron is the 4th most abundant element in the Earth's crust, so its presence in trace quantities on any rock surface is not surprising. Manganese is less common. It makes up roughly 0.1% of the Earth's crust by mass, but it is still widely distributed, present in soils and sediments almost everywhere. What is surprising, and what will become the central chemical puzzle of this story, is what happens to these trace amounts of manganese once they arrive on the surface of a varnished rock. They do not stay dissolved. They do not wash away with the next rain. Instead, they are transformed into something solid, something insoluble, something that stays put and accumulates. And the concentration of manganese in black desert varnish relative to its concentration in the surrounding environment is not slightly elevated. It is 50 to 60 times higher than in the Earth's crust. In some samples, it is 300 times higher than in the surrounding soil. Something on the surface of the rock is selecting manganese out of dilute solution and holding on to it. The question of what that something is, whether it is a purely chemical process or whether it requires the participation of living organisms, has occupied researchers for decades, and the answer remains genuinely uncertain. But before we reach that question, it is worth pausing on the timescale of what is happening here. Desert varnish accumulates at a rate of between 1 and 40 micrometers per 1,000 years, 1 to 40 millionths of a meter per 1,000 years. At the slow end of that range, a coating that has been building for 10,000 years, since roughly the end of the last ice age, since roughly the time humans were first developing agriculture in the Fertile Crescent, would be 10 micrometers thick. That is about 1/7 the width of a human hair. At the faster end of that range, 10,000 years of accumulation might give you 400 micrometers, still less than half a millimeter. A coating that has reached the thickness of a single sheet of paper, roughly 100 micrometers, may represent anywhere from a few thousand to 50,000 years of deposition, depending on local conditions. These numbers are worth sitting with for a moment, because they are so far outside the scales at which human life operates that they are almost impossible to feel. From the earliest writing in Mesopotamia to this present night, covers roughly. In that time, in a typical desert environment, desert varnish has grown by perhaps 50 to 200 micrometers. You could not see that growth. You could not measure it without a microscope. And yet it is happening continuously on every stable rock surface in every dry place on Earth, with a patience that makes 5,000 years of human civilization seem like a brief afternoon. The dust settles, the ions arrive, the clay holds them, and something, chemistry or life or both, begins to work. To understand why desert varnish turns black, you need to understand what happens to a manganese atom when it loses an electron. This is the chemistry at the heart of everything, and it is worth going into carefully, because once you see it clearly, the whole process becomes beautifully logical. Manganese, like iron, is what chemists call a transition metal. These are the elements that sit in the middle of the periodic table, and what distinguishes them from other elements is that they can exist in several different states of electrical charge. An atom, in its neutral state, has equal numbers of protons in its nucleus and electrons orbiting around it, so the positive and negative charges cancel out. But electrons can be removed from atoms or added to them, and when that happens, the atom becomes an ion carrying a net, positive or negative charge. The process of removing electrons is called oxidation. The process of gaining electrons is called reduction. These two processes always happen together. Whenever one atom loses electrons, another gains them. Manganese in natural water, in rainwater, in dew, in the thin films of moisture that wet a rock surface after a brief desert shower, typically exists in what is called the +2 state, meaning each manganese atom has lost 2 of its electrons and carries a charge of +2. In this form, manganese is soluble. It dissolves in water readily and moves with it, carried wherever the water goes. If nothing else happened, the manganese arriving on a rock surface dissolved in rainwater would simply wash away again when the water evaporated or drained off. But something else does happen. The manganese is oxidized further. It loses additional electrons, moving from the +2 state to the +3 or +4 state. And at that point, everything changes. Manganese in the +4 state forms a compound with oxygen called manganese dioxide, and manganese dioxide is essentially insoluble in water. It does not dissolve. It does not flow away. It precipitates, falls out of solution as a solid, and stays where it is, and manganese dioxide is black. This is why black desert varnish is black. It is not a surface stain. It is not a biological pigment. It is the color of an insoluble manganese compound that has been precipitated onto and into a clay matrix on the surface of the rock, and that color, that deep, dense, almost mineral black, is one of the most stable things in the natural world. Manganese dioxide does not bleach in sunlight. It does not dissolve in rain. It does not evaporate in heat. Once it forms, it stays. Now, the question of what drives that oxidation, what takes manganese from its soluble +2 form to its insoluble +4 form, is precisely where the science becomes most interesting. And to understand it, you need to understand one more thing about the clay minerals that form the bulk of the varnish. Clay mineral surfaces are not electrically neutral. As we established in the previous chapter, the substitution of atoms of different sizes within the crystal lattice leaves the surface with a net negative charge in most clays. And because opposite charges attract, these negatively charged clay surfaces strongly attract positively charged ions, including the manganese ions dissolved in surface moisture. The clay surface acts as a concentrating mechanism, drawing manganese ions out of their dilute solution and holding them close against the mineral surface in far higher concentrations than they would achieve in open water. This concentration effect is important because many chemical reactions, including oxidation reactions, proceed faster when the reacting molecules or ions are close together. By pulling manganese ions onto its surface, the clay is, in a sense, setting up the conditions for the next step. The manganese is no longer dilute and dispersed. It is concentrated, held in place, and ready to react. Iron undergoes a similar process, though the chemistry differs slightly. Iron in water also typically exists in a +2 soluble form. When it is oxidized to the +3 state, it too forms insoluble oxides and hydroxides, compounds like hematite and goethite, which are various shades of red, orange, and brown. This is the chemistry of rust, operating on a rock surface rather than on a piece of steel, and it explains the orange and reddish tones of iron-rich varnish. The gradient of color across a canyon wall, from orange at the margins, through brown in the middle range, to deep black in the oldest and most fully developed sections, reflects the relative proportions of iron and manganese compounds in the varnish. Where iron dominates, the surface is red or orange. Where manganese has been concentrated and oxidized over longer periods or under more favorable conditions, the surface darkens toward black. And the conditions that favor manganese concentration over iron concentration are primarily alkaline ones. Environments where the local chemistry of the rock surface, modified by the slow accumulation of minerals and the occasional passage of moisture, shifts above a pH of around 7, meaning slightly alkaline rather than neutral or acidic. Below that pH threshold, in more acidic microenvironments, manganese oxidizing processes are less efficient and iron dominates. This is why the character of varnish varies not just between different canyon walls, but between different parts of the same wall. A ledge that collects slightly more rainwater may develop a different chemistry from the vertical face below it. A surface that receives more direct sunlight may heat and cool more dramatically, affecting the evaporation rate of surface moisture and therefore the concentration of ions at the critical moment when oxidation occurs. The extraordinary enrichment of manganese in black varnish, 50 to 60 times its average crustal abundance, tells you something profound about the selectivity of this process. It is not simply that manganese happens to be present and happens to end up in the varnish. Something is actively selecting it, concentrating it, and transforming it. The clay matrix provides the scaffold and the concentrating mechanism. The oxidation chemistry provides the lock that holds the manganese in place once it arrives. And the whole structure, layers of clay minerals with manganese and iron oxides precipitated within and between them, hardens over time into a material that is genuinely difficult to break down, resistant to the same weathering processes that would slowly dissolve the bare rock beneath. There is something almost architectural about it. The clay provides the framework, the iron and manganese provide the binding material, and the whole assembly grows by accretion, one invisible layer at a time, in a structure that is simultaneously very thin and very strong. A cross-section of well-developed desert varnish, examined under a powerful microscope, reveals distinct laminations, alternating dark and light bands, each one representing a different period of deposition under different climatic conditions. It looks, under that magnification, almost like a very fine geological formation, which is exactly what it is. But there is one more element to this chemistry that has not yet been fully explained, and it is the most contested element of all. The oxidation of manganese from its +2 to its +4 state does not happen spontaneously and easily in the conditions found on a desert rock surface. In pure water, at typical desert temperatures and pH values, the reaction is slow. Thermodynamically, it is favorable, meaning the chemistry wants to go in that direction. But kinetically, it is sluggish. Something appears to be accelerating it. And one of the most compelling candidates for that accelerator is not a mineral at all. It is alive. In 1981, a paper appeared in the journal Science that changed how geologists thought about desert varnish. Its authors were Ronald Dorn and Theodore Oberlander, working in the arid landscapes of California, and their argument was both elegant and provocative, that the extraordinary concentration of manganese in desert varnish was not the product of pure chemistry operating on a bare mineral surface, but was instead the work of living organisms, specifically of bacteria capable of extracting energy from the oxidation of manganese itself. The idea was not entirely new. Researchers had noticed microorganisms on varnished surfaces before, but Dorn and Oberlander assembled the evidence into a coherent hypothesis and gave it a clarity that made it impossible to ignore. And in doing so, they opened one of the most productive and most genuinely unresolved debates in desert geoscience. The core of the microbial hypothesis rests on a beautiful piece of biochemistry. Most organisms on Earth extract energy from chemical reactions involving carbon compounds, the burning of sugars, essentially, in one form or another. But a smaller group of organisms, sometimes called chemolithotrophs, a term that means, roughly, organisms that eat rock chemistry, extract energy from purely inorganic reactions. They oxidize metal ions the way other organisms oxidize food, capturing the energy released by that electron transfer and using it to drive the chemical reactions of life. Manganese oxidizing bacteria are among the most remarkable of these. The specific reaction they catalyze is the one we discussed in the previous chapter, the conversion of dissolved manganese in the +2 state to solid manganese dioxide in the +4 state. Each manganese atom that undergoes this transformation releases a small amount of energy as electrons move from one state to another, and the bacteria are able to capture a portion of that energy and use it to grow, reproduce, and carry out all the other business of living. The manganese dioxide that results from this reaction is deposited outside the bacterial cell, forming a coating around and between the cells that gradually builds up into the dark laminated layer we recognize as varnish. Two bacterial genera have been most frequently identified on varnish surfaces and implicated in this process. The first is Metallogenium, a genus of organisms that forms distinctive star-shaped or filamentous structures and has been observed producing manganese oxides in laboratory cultures. The second is pedomicrobium, a budding bacterium that attaches itself to surfaces and produces manganese oxide deposits around its cell body. Both have been found in samples taken from desert varnish in multiple locations around the world. Their presence on the varnish surface is well documented. What remains debated is whether their presence is the cause of the varnish or merely a consequence of it, whether they are building the dark layer or simply living in it. This distinction matters enormously. If manganese oxidizing bacteria are the primary drivers of varnish formation, then desert varnish is fundamentally a biological phenomenon, a product of life operating in one of the most extreme environments on Earth, finding a way to survive in a place of intense heat, desiccation, and ultraviolet radiation by building its own protective mineral housing. That would make varnish a kind of biomineralization, in the same broad category as the process by which mollusks build shells or corals build reefs. It would mean that the dark coating on a canyon wall is, in a deep sense, alive, or at least is the accumulated product of life. The conditions on a varnished rock surface are, from the perspective of most organisms, extremely hostile. Desert rock surfaces can reach temperatures of 70 degrees Celsius or more in direct sunlight. They dry out completely between rainfall events, which in some desert environments may be separated by months or years. They are exposed to intense ultraviolet radiation, which damages DNA and disrupts the chemistry of living cells. And yet, bacteria have been found alive and metabolically active in desert varnish. They are not thriving in the way bacteria thrive in a warm, moist, nutrient-rich environment. But they are there, persisting, protected to some degree by the mineral matrix that surrounds them, surviving the intervals between moisture events in dormant states and resuming activity when water briefly returns. The clay matrix itself may play a role in making this survival possible. The flat sheet structure of clay minerals, with its stacked layers and its large internal surface area, creates a microenvironment within the varnish that retains moisture longer than the bare rock surface would. It provides a kind of shelter, not comfortable by any ordinary standard, but marginally less lethal than the open surface in full desert sun. And the manganese dioxide deposited by the bacteria forms a crust over the whole assembly that provides some protection from the most intense ultraviolet radiation. But the microbial hypothesis has been challenged, and the challenges are serious enough that the question cannot be considered settled. In 2008, a microscopy study proposed that desert varnish could be reproduced in the laboratory through chemistry that did not involve living organisms at all. The researchers suggested that silica, silicon dioxide, the main component of quartz and many common minerals, might play a more central role than previously appreciated, acting as a binding agent that could trap and preserve organic compounds without requiring metabolically active bacteria to produce the manganese enrichment. This model proposed that the organic material found in varnish might be incorporated passively, bacteria and other organic particles simply becoming embedded in a mineral coating that was growing through purely chemical means. Then, in 2019, a research group added another layer of complexity with what they called a photo-oxidation model. The key observation was that when sunlight falls on the surface of metal oxides, including the manganese and iron oxides already present in developing varnish, it can generate reactive oxygen species. Reactive oxygen species are molecules or fragments of molecules that carry an unpaired electron, making them chemically extremely aggressive. They react readily with almost anything nearby, including dissolved manganese ions. The researchers detected these reactive oxygen species in varnish suspensions and demonstrated in laboratory simulations that this photocatalytic process, the use of light energy absorbed by metal oxides to drive the oxidation of manganese, could proceed at meaningful rates without any biological involvement whatsoever. This finding is significant for several reasons. It suggests that the same sunlight that makes desert surfaces so hostile to life might also be directly driving the chemistry that produces the varnish. It offers a mechanism by which manganese oxidation could be accelerated on a rock surface without requiring bacteria. And it raises the possibility that on other planets where sunlight is present, but life may not be, similar processes could operate. The current state of understanding is that both pathways, biological and abiotic, meaning non-living, are probably real and probably operating simultaneously on most varnish surfaces. The relative contributions of each may vary with local conditions. In environments where the surface pH is above about 7.5, manganese oxidizing bacteria are less active and the abiotic pathways may dominate. In more neutral or slightly alkaline conditions, the bacteria may play a larger role. Temperature, moisture availability, the frequency of wetting events, and the specific mineral composition of the underlying rock all influence which pathway predominates. What this means in practice is that desert varnish is not a single phenomenon with a single cause. It is a family of related phenomena, sharing a common appearance and composition, but potentially arising through different combinations of chemistry and biology, depending on where you are standing and what the conditions are like on the particular rock face you are looking at. The dark coating on a wall in Utah may have formed through somewhat different processes than the dark coating on a rock in the Sahara, even though they look nearly identical from a few meters away. There is something fitting about that complexity. A process that operates over tens of thousands of years in an environment that changes with every season and every decade should perhaps not be expected to have a single, simple mechanism. The desert is patient. The chemistry is patient. And the question of exactly how it all works is still, quietly, being answered. If you were to take a very thin slice through a well-developed section of desert varnish, a cross-section, perhaps 0.5 millimeter thick, cut perpendicular to the rock surface and examined under a powerful microscope, what you would see is not a uniform dark smear. Distinct, alternating bands of different color and composition, stacked one on top of another like the pages of a very old and very thin book. Dark bands, rich in manganese oxide. Lighter bands, orange and yellow, richer in iron. And within those broader alternations, finer variations still, subtle shifts in the density of clay minerals, in the concentration of trace elements, in the texture of the crystalline structure. Each of these bands is a chapter. Each one represents a different period of time, a different set of environmental conditions, a different climate, and scientists have spent decades learning to read them. The principle behind this reading is straightforward once you understand the chemistry. Manganese is concentrated in varnish, primarily during periods when moisture is more available, when rainfall is more frequent, when dew forms more often, when the rock surface is wet for longer intervals. This is because manganese arrives dissolved in water and is concentrated and oxidized at the surface when water is present. More moisture means more manganese delivery, more oxidation events, more dark manganese dioxide deposited. The result, over a period of centuries or millennia of relatively wet conditions, is a dark manganese-rich lamination in the varnish record. During drier periods, the manganese supply diminishes. The rock surface dries more quickly after each moisture event, giving less time for manganese oxidation to proceed. Iron, which is slightly less sensitive to these conditions, continues to accumulate, and the varnish deposited during dry intervals is correspondingly richer in iron oxides, lighter in color, tending toward orange and yellow rather than black and brown. The technique of reading these layers is called varnish microlamination dating, sometimes shortened to VML. It was developed over several decades of careful work by researchers studying desert surfaces in the American Southwest, and it works by correlating the sequence of dark and light bands visible in a varnish cross-section with independently established records of past climate change. Once, a particular sequence of wet and dry periods has been identified in the climate record through other means, through pollen analysis, through lake sediment cores, through the growth rings of ancient trees. The same sequence should appear as a corresponding pattern of dark and light laminations in varnish that was forming during those same periods. By matching the patterns, researchers can assign approximate ages to particular laminations and, by extension, to whatever rock surface or archaeological feature that Varnish was coating. It is genuinely analogous to reading tree rings. A dendrochronologist, someone who studies tree ring sequences, can look at the growth rings in an ancient piece of timber and identify within them the signatures of particular drought years, particular wet years, particular climate events that appear in the ring record of trees across a wide region. The tree rings are a biological archive of climate, written in the language of growth and stress. Varnish microlaminations are a mineralogical archive of climate, written in the language of manganese and iron. The American Southwest has been particularly well studied through this technique, because the region has experienced dramatic climate shifts over the past 12,000 years, and because the desert surfaces there are among the most extensively varnished on Earth. The transition out of the last ice age, which ended roughly 11,000 years ago, left clear signatures in varnish records from Utah, Arizona, and California, a period of relatively wet conditions associated with the retreat of the glaciers and the redistribution of atmospheric moisture patterns, followed by a drying trend in the middle, Holocene, and then a return to somewhat wetter conditions in the late Holocene, before the current period of aridity. These broad patterns are visible in the lamination sequences of varnish samples taken from stable rock surfaces across the region, providing a continuous record of environmental change that complements and extends the information available from other climate proxies. There is a second dating technique that works through a different but related principle. It is called cation ratio dating, and it was developed in the early 1980s by Ronald Dorn, the same researcher whose work on manganese oxidizing bacteria helped establish the microbial hypothesis. The term cation simply means a positively charged ion, and the technique is based on the observation that different cations behave differently within the varnish over time. Some elements, when they arrive in the varnish as dissolved ions, are relatively mobile. They can continue to move through the varnish structure as it ages, gradually leaching out and being replaced or lost. Titanium, by contrast, is extremely stable within the varnish matrix. It arrives, it is incorporated, and it essentially stays put for the entire lifetime of the coating. As varnish ages, the ratio of mobile elements like potassium and calcium to stable elements like titanium therefore decreases. The mobile elements slowly leak away while the titanium remains. The older the varnish, the lower the ratio of mobile to stable cations. By measuring this ratio in a varnish sample and comparing it to a calibration curve established from varnish samples of known age, it is possible to estimate the age of the varnish, and therefore the age of the surface it coats. If that surface was exposed by a rockfall, or by a landslide, or by the carving of a petroglyph, then the age of the varnish that has formed since that exposure gives you a minimum age for the event that created the exposure. Neither technique is without its complications. The cation ratio method has been criticized for assuming a constant rate of cation leaching across different environments, when in fact that rate may vary with temperature, moisture, and the specific chemistry of local groundwater. Varnish microlamination dating requires a well-established regional climate chronology to calibrate against, and in parts of the world where that chronology is less complete, the technique is less precise. Both methods are subject to the variability in varnish formation rates that makes all varnish-based chronology somewhat uncertain. But despite these limitations, varnish dating has produced results of genuine significance. Studies of varnish microlaminations from the American Southwest have revealed the timing and duration of Holocene, wet and dry periods with a resolution that other techniques cannot match in the same environments. These records are being used to calibrate climate models, the computational tools that scientists use to project how temperature and rainfall patterns will change in the future, by testing those models against a climate history that extends far beyond the period covered by instrumental weather records. If a model can accurately reproduce the pattern of wet and dry periods visible in a 50,000-year Varnish record, that is evidence that the model's underlying physics is sound. If it cannot, that is information about what the model is missing. In this way, the thin, dark skin of a canyon wall in Utah is contributing, very quietly, to our understanding of what the climate of the American Southwest might look like a century from now. The past is being read layer by invisible layer and used to illuminate the future. There is something deeply satisfying about that, the idea that a coating thinner than a human hair, built over thousands of years by dust and chemistry and the occasional passage of moisture, should turn out to be one of the more useful tools available for understanding where the world's climate is heading. The varnish does not know any of this, of course. It simply accumulates, one layer at a time, in the dark and the heat and the long desert silence. There is a place on the western edge of Albuquerque, New Mexico, where a long ridge of dark volcanic basalt rises above the desert floor like the spine of some enormous buried creature. The rock is old. The basalt was extruded from a series of volcanic vents somewhere between 150,000 and 180,000 years ago, and its exposed surfaces have been darkening with desert varnish for most of that time. The coating on the oldest, most stable faces is deep and glossy, built up over millennia into a surface as dark as polished obsidian. This place is called Petroglyph National Monument, and it contains more than 25,000 individual carvings. They were made, most of them, by the ancestral Puebloan peoples who lived in this region for thousands of years before European contact, with a smaller number added by Spanish settlers in the colonial period. The method of their creation was simple and direct. A stone tool held in the hand struck against the dark varnished surface of the basalt with enough force to chip away the outer coating and expose the lighter grey rock beneath. The contrast between the dark varnish and the pale fresh rock is sharp and immediate. You can see it from 50 meters away. A single skilled stroke of the tool could define a line. A series of careful strikes could produce a spiral, an animal, a human figure, a series of geometric forms whose meaning we can sometimes infer and sometimes cannot. The images at Petroglyph National Monument range from the recognizable to the mysterious. There are bighorn sheep, their curved horns rendered with a few confident lines. There are spirals that may mark the passage of the sun through solstice and equinox. There are human figures with elaborate headdresses and masks, and abstract geometric patterns that repeat across dozens of panels. There are images that clearly depict animals, birds, lizards, insects, and others that seem to reach towards something less tangible, some cosmological or ceremonial significance that the stone preserves but does not explain. But the story of human engagement with desert varnish does not begin in New Mexico, and it does not begin with the ancestral Puebloans. It reaches much further back. In the Libyan desert, in a remote and largely waterless region of what is now southwestern Libya, there is a site called Wadi Mathendus. A wadi is a dry riverbed, a valley carved by water that no longer flows, and Mathendus is one of the most remarkable rock art sites in the world. The canyon walls there are covered with engravings, not painted, but incised into the rock surface in the same basic way as the petroglyphs of New Mexico, depicting animals that have not lived in that region for thousands of years. There are crocodiles, there are hippopotamuses, there are giraffes and elephants and cattle, and, most movingly, a large and carefully rendered image of two rhinoceroses, their bodies facing each other across a few meters of ancient stone. These animals tell a story about climate because they require water and vegetation that the Libyan desert has not supported for a very long time. The presence of crocodiles and hippos in particular implies a landscape with permanent water sources, rivers or lakes, that existed during a period geologists call the African Humid Period, a time roughly between 11,000 and 5,000 years ago when changes in the Earth's orbital geometry caused a significant increase in monsoon rainfall across North Africa. The Sahara was not, during this period, the barren, hyper-arid landscape it is today. It was grassland and savanna, threaded with rivers and dotted with lakes, inhabited by the full range of large African fauna and by the human communities who hunted and herded among them. The engravings at Wadi Muthandas are estimated to be around 8,000 years old, placed in the middle of this humid period when the artists who made them were surrounded by the very animals they depicted. They were not recording something exotic or distant. They were recording their world. What connects these images to the science of desert varnish is the question of re-varnishing. When a petroglyph is made, when the dark surface is chipped away to reveal the pale rock beneath, the exposed fresh surface immediately begins to accumulate new varnish. Dust settles on it. Ions arrive in moisture. The chemistry begins again, from the beginning. Over time, the pale scar of the carving begins to darken, slowly and unevenly, reacquiring the coating that was removed. The rate of this revarnishing depends on local conditions, climate, aspect, the specific mineralogy of the exposed rock, but it follows the same broad trajectory as the original varnish formation. This re-varnishing is what makes it possible, in principle, to date petroglyphs. The varnish that has grown back over the carved surface since the moment of carving represents a minimum age for the carving itself. If the re-varnished surface can be sampled and analyzed using the cation ratio method or the microlamination technique or a combination of approaches, an estimate of the carving's age can be obtained. The technique is not without its difficulties. Sampling varnish from a petroglyph surface requires removing a tiny fragment of the coating, which is itself an act of minor destruction. The dating methods carry significant uncertainties. And there is always the possibility that a surface was recarved at a later date, resetting the varnish clock while leaving an image that appears ancient. But despite these complications, varnish dating has provided age estimates for petroglyphs at sites across the American Southwest and North Africa that are broadly consistent with other lines of evidence. The archaeological record, the presence of depicted species, the paleoclimatic context, and that extend the known timeline of human rock art in some regions significantly further back than other methods can reach. There is something worth dwelling on in the human dimension of this. The people who made the images at Wadi Muthandas were not thinking about desert varnish. They were not thinking about manganese oxidation or cation ratios or climate archives. They were thinking about the rhinoceros in front of them and about whatever it meant to them to press the image of that animal into the dark stone wall of a canyon that has since been dry for 5,000 years. They chose the dark surface because it gave them contrast, because the pale rock beneath made their images visible from a distance, because the varnish was already there, already dark, already ready to serve as a background. They were using the same material that we are now using to understand their world. And the stone has held both things simultaneously ever since. The human image carved into its surface and the slow geological record growing back over it, layer by layer in the dark. 8,000 years of new varnish accumulating over 8,000 years of old image. The rock does not distinguish between them. It simply holds everything that has happened to it, quietly and without preference, the way stone does. The varnish at the edge of a petroglyph's carved line, where the dark coating meets the pale exposed rock, is one of the few places in the world where you can stand at the precise boundary between geological time and human time, between the deep, slow processes of the mineral world and the brief, vivid flash of human intention. The carving happened in a moment. The varnish has been answering it very slowly ever since. In the years since the first successful Mars landers touched down on the red planet's surface, One of the persistent puzzles in the images they returned has been the appearance of the rocks around them. Many Martian rocks are dark. Not uniformly dark, not dark in the way of freshly exposed basalt, but dark in a streaky, coating-like way that is reminiscent, to geologists who have spent time in Earth's deserts, of varnished surfaces, dark films on rock faces, streaks running downward from ledges, following the paths that water would take if water were there. Surfaces that appear, in the images from orbiters and rovers, to have a skin. Whether these Martian surface coatings are truly analogous to terrestrial desert varnish is a question that has not yet been definitively answered. The chemical analyses available from Mars landers and rovers suggest that the surface chemistry of these dark coatings differs in some respects from Earth's varnish. The manganese enrichment that is so characteristic of black terrestrial varnish has not been unambiguously confirmed on Mars, though some rover measurements have hinted at localized manganese concentrations that are elevated above background levels. The picture is incomplete because the instruments available to us on Mars are limited, and because the planet's surface is vast and varied in ways that a handful of landing sites cannot fully characterize. But the question of whether something like desert varnish could form on Mars is genuinely important, and studying terrestrial varnish has given planetary scientists tools for thinking about it carefully. Consider first the abiotic photooxidation pathway described in Chapter 4. The 2019 research that identified reactive oxygen species as drivers of manganese oxidation on Earth's varnish surfaces was significant in part because it pointed toward a mechanism that does not require liquid water or living organisms to be continuously present. It requires only two things: metal oxides already present on the surface and sunlight. Mars has both. Its surface rocks are rich in iron oxides. The compound that gives the planet its characteristic reddish color is essentially rust, iron oxide in a form called hematite. Manganese is also present in Martian rocks and soils, detected in multiple locations by rover instruments. And sunlight, while less intense at Mars's greater distance from the Sun than at Earth's surface, is present and includes significant ultraviolet wavelengths that are particularly effective at driving photocatalytic reactions. Photocatalysis is the process by which light absorbed by a material drives a chemical reaction that would not otherwise proceed at a meaningful rate. In the context of varnish chemistry, the metal oxides in the developing coating absorb photons of sunlight and use that energy to generate reactive oxygen species, highly reactive molecular fragments carrying unpaired electrons that can then oxidize dissolved manganese or ions. On Earth, this process operates alongside microbial activity and the physical concentration of ions by clay minerals. On Mars, where liquid water is currently absent from the surface in any sustained form, the purely physical and photochemical aspects of varnish formation might still operate, albeit slowly and in a modified form. What this means for astrobiology, the study of the possibility of life elsewhere in the universe, is that the presence of dark surface coatings on Martian rocks cannot by itself be taken as evidence of biological activity. The photooxidation model demonstrates that the chemistry can proceed without life. But conversely, if the microbial pathway is real and significant on Earth, then the coatings on Martian rocks might, in principle, preserve chemical or physical signatures that would distinguish biologically influenced varnish from purely abiotic varnish, if we knew what signatures to look for and had instruments sensitive enough to detect them. This is where the study of terrestrial varnish becomes directly relevant to planetary science. The specific patterns of elemental enrichment in biologically produced varnish, the characteristic lamination structure, the particular ratios of carbon compounds to mineral material, the distribution of trace elements that reflects microbial metabolism rather than purely chemical precipitation, might serve as biosignatures, meaning chemical or structural markers that indicate the past or present involvement of living organisms. Researchers studying Earth's desert varnish are, among other things, trying to identify which of its properties are uniquely biological and which could arise through purely abiotic processes, precisely because that distinction will matter enormously when more capable instruments eventually reach the Martian surface. There is a rover currently operating on Mars, Perseverance, whose instrument suite includes tools capable of detecting organic molecules and analyzing rock surface chemistry at a level of detail not previously possible from a rover. Among the surfaces it has been examining are dark-coated rocks in Jezero Crater, a location chosen in part because it appears to be the site of an ancient lake delta, a place where water once stood and where, if life ever existed on Mars, it might have left traces. Whether any of the dark coatings Perseverance encounters will turn out to be something meaningfully analogous to terrestrial desert varnish remains to be seen. The data analysis is ongoing. But the conceptual link between a varnished canyon wall in Utah and a dark-coated boulder in a Martian crater is not fanciful. Both involve the interaction of metal oxides with the environment over long timescales. Both raise the question of whether life is necessary for the process or merely one possible participant in it, and studying one helps us think more clearly about the other. There is something quietly extraordinary about that connection. A coating that has been slowly building on desert rocks since before humans existed, a coating that indigenous peoples used as a canvas, that Darwin scraped samples from, that geologists have argued about for decades, turns out to be one of the best analogues available for understanding the surface chemistry of another planet. The thin, dark skin of a boulder in the American Southwest is, in a sense, a window onto Mars. Not a perfect window, not an unambiguous one, but a real one. A place where the same fundamental chemistry, dust, metal ions, oxidation, time, has been playing out under conditions that overlap with what we observe across 48 million miles of space. The universe, it turns out, has a limited repertoire of chemistry. The same reactions that slowly darken a cliff face in the Colorado Plateau are available in modified form on a cold, dry world orbiting further from the same star. The process does not require our presence to proceed. It does not require our understanding. It simply requires the elements and the light and the time. The light is changing. In the late afternoon in Canyon Country, the shift happens gradually and then all at once. The sun drops toward the canyon rim, and the shadows that had been lying flat and sharp across the rock face begin to stretch and soften. The varnished surface, which caught the full midday light with a particular hard gloss, now catches the lower-angled light differently. The dark streaks seem to deepen. The glossy patches seem to hold more warmth. The whole wall takes on a quality that is almost liquid, as though the darkness is not a coating on the rock, but a depth within it. It is worth returning here to this wall, at the end of everything we have covered. A coating thinner than a human hair, built from dust carried on the wind, from places that may be thousands of kilometers away, held in place by electrical forces operating at the scale of individual atoms, darkened by manganese that has been pulled from dilute solution, concentrated 50 times above its natural abundance, and locked into an insoluble black compound by chemistry that may be purely mineral or may involve the patient metabolic work of bacteria too small to see. Layered into a record of wet years and dry years, of ancient climates and vanished lakes, of the long oscillation of Earth's environment over timescales that make the entire span of human civilization look like an afternoon. And carved into, here and there, by human hands, by people who stood at this same wall, in this same light, and saw what we see, a dark surface, a pale rock beneath, a contrast that could be made to carry meaning. 50,000 years for the thickness of a sheet of paper. That number keeps returning, and it is worth letting it settle fully. The oldest anatomically modern human fossils we have found are roughly 300,000 years old. Writing was invented roughly 5,000 years ago. The entirety of recorded human history, every war, every empire, every poem, every scientific discovery, every city built and abandoned, fits inside 5,000 years. Desert varnish, in some of its thicker expressions, has been accumulating for 10 times that span, 100 times that span. In the right conditions, a single varnish deposit might have been growing continuously since before our species existed. And it does not hurry. This is perhaps the most fundamental thing about it, and the thing that is hardest to hold in mind in the ordinary rhythm of daily life. The dust does not hurry. It settles when the air is still enough to let it settle, and it stays where it lands because the electrical forces on the clay surface are strong enough to hold it, and it accumulates because each new particle that arrives finds a surface already prepared to receive it. They arrive dissolved in a film of dew, and they are drawn to the charged clay surface by forces they do not experience as forces, and they are oxidized by chemistry that proceeds at whatever rate the temperature and pH and light conditions allow, and they precipitate as black manganese dioxide because that is what the chemistry does. The bacteria, if they are there, do not hurry either. They metabolize when moisture is present and go dormant when it is not, and their contribution to the varnish accumulates over generations too numerous to count, in a process that has no awareness of its own timescale. The rock does not hurry. It has been here for millions of years. It will be here for millions more. The varnish on its surface is, from the rock's perspective, a recent development, a thin and temporary coating that happens to be accumulating just now, in this particular geological moment. There is something quietly sustaining in that, not because geological patience is something we can straightforwardly emulate. Human lives are short, and the things that matter to us are urgent in ways that dust settling on a canyon wall is not. But because the existence of such processes, going on continuously and without urgency in every dry and sun-warmed place on Earth, is a reminder that the world is vastly larger and slower and more patient than the portion of it we inhabit. Whatever you are carrying tonight, whatever accumulated weight of the day or the week or the longer span of difficulty that does not resolve as quickly as you would like, it is happening inside a world that has been doing this for 50,000 years per sheet of paper and will continue doing it long after every concern that feels pressing tonight has been forgotten. The desert does not know about urgency. The chemistry does not know about urgency. The slow accumulation of dark material on the face of a sunlit cliff is not in a hurry to be finished, because it is never finished. It simply continues, one invisible layer at a time, in the silence between rainstorms, in the heat of the afternoon, in the long, cold desert nights when the temperature drops 40 degrees from its daytime high and the rock contracts slightly and the thin varnish shifts with it, barely, without cracking, holding. The streaks on the canyon wall descend like the memory of 1,000 rainstorms. Each one marks a path that water took, perhaps once a decade, perhaps once a century, carrying its dissolved cargo of manganese and iron down the face of the rock and leaving a trace behind. The trace darkens over time. It becomes part of the wall's character, part of what the wall looks like from a distance, part of what a person standing at its base in the fading afternoon light sees and feels without being able to fully articulate. What they feel, perhaps, is something like the weight of time. Not a heavy or oppressive weight, but the weight of depth, the sense that what you are looking at has been here for longer than you can really hold in your mind, and that it will continue after you are gone, and that this continuity is not indifferent so much as simply vast. The varnish does not care about you, but it also does not exclude you. You are standing at the same wall where someone stood 8,000 years ago and pressed a stone tool into the dark surface and made an image of a rhinoceros or a spiral or a hand. You are standing in the same light that has been driving the photo-oxidation of manganese since before that person was born. You are breathing the same dry air that carries the same clay particles that have been settling onto this surface for longer than our species has existed. The layer being deposited tonight, the few atoms of manganese being oxidized right now, in this moment, by the last light falling on this wall, is thinner than anything we can measure in ordinary life. It is a fraction of a nanometer. It is nothing by any human scale. And it is also the newest chapter in a record that began before the glaciers retreated, before the Sahara was green, before anyone thought to carve an image into the dark skin of a canyon wall and leave it for someone else to find. The sentences are growing shorter now. The light is almost gone. The wall stands in the dusk, darker than the sky behind it. The varnish holds whatever warmth the rock absorbed through the long afternoon. The streaks descend, patient and still. Somewhere in the clay, in the spaces between the flat crystal sheets, a manganese ion is settling into place. It will still be there in 10,000 years. The dust settles. The chemistry continues. The record grows, one invisible layer deeper. And so we leave it there, the wall standing in the dark, the varnish darkening with it, the whole slow process going on without us, as it always has. Drift now, if you're ready. Sleep well.